topic we've already talked about, just in kind of a different way, more deeply really. We're going to explore another way of thinking about autonomous first order ODEs, okay? So as we get started, let's just think about what does this mean? Again, if we write y prime is some function of what? Is there any ambiguity what to write? No, right? If we're talking about autonomous first order ODEs, then y prime is some function of y, right? Because what would be the dependent variable? Y. The independent variable doesn't appear, so we could make it up to be anything we want it to be, right? The independent variable could be x, so this could be y prime as a function of x is some function of y, or the independent variable could be t, which is often what we use. So we'll write it out here. dy dt in this case is some function of y. Here, right, the dependent variable is y. That was the case up there as well. And now we've identified that we're going to pick t as our independent variable instead of x for a variety of reasons. One for just a little variety, right? And the other is just because this is often used in population dynamics. Dynamics of a population. Dynamics just means change, right? How populations change, okay? And so y of t would be the number of individuals in that population at any time t. But oftentimes what also gets used and what the way our book utilizes these problems is it's going to go with an x for the population, right? And so instead we'll proceed with x as the dependent variable and t still as the independent variable. Okay? And so how do I write an autonomous first order ODE, or general autonomous first order ODE in this context? Good. The derivative of x with respect to t is f of x, right? Now, remember, right, if I'm talking about dependent variable, independent variable, right, a coordinate system, then what's on the horizontal axis here? Good, t. And the vertical axis? Yes, y. Nice. And so if I'm here and I'm thinking about coordinate system, then what's the horizontal axis? T. And what's the vertical axis? X, right? So this is one of the reasons why I will often use this formulation instead, because it at least keeps you thinking more. And whenever we talk about the x-axis, if we're using this notation, right, x is the vertical axis, the dependent variable axis, right? Okay, good. All right, so let's see. So another way to then talk about that in a simpler way, right, here is to just say x prime equals f of x. It's the exact same thing, okay? So don't be afraid of that, right? It means this, yeah? Just be really clear here. Can we just integrate both sides? Absolutely not, right? If we're going to integrate this guy to get out x of t, right, then we're integrating with respect to t. That's what gives us x of t. We can't integrate this with respect to t because it depends on x, and x is a function that depends on t, right? Our unknown variable, unknown function, is x as a function of t, right? So if this was an f of t, this would not be an autonomous equation, but it would be just a simple calc 1, calc 2 integration, right? Okay? It's not an t, it's an x. That makes it a differential equations problem, right? Okay, so where have we seen such things? Population dynamics. Where have we seen these already? Right? This is not new. None of this is new, really. Where have we already seen it? What are some of the autonomous equations we've already talked about, right? For population type dynamics. Well, exponential growth or decay, right? That was one, yeah? Oops, is that my phone? I better turn that off. Okay, so that was one, right? How did we think about it? Y prime is equal to ky. I think that's how we first talked about it, right? Y prime is equal to ky. Where else have we seen a y prime equals some function? Let's think about, we've been talking about y. What else did we see that was y prime, that was some model that was y prime with some function of y? Let's write it. Y prime is some constant times, instead of just plain old y, a minus y. Have we not seen that? Maybe we'll rewrite it with different letters, right? How about dt? Oh, is it making some sense now? Yeah, is it coming back? Do I hear it? Do I hear it? What is this? Right, is equal to k times a minus t. Are these not the exact same equation? Just one uses a y as the dependent variable and one uses a t. What is this, right? This is Newton's law of cooling. Right? Okay? Newton's law of cooling, NLC. Right? Newton's law of cooling. Yes? Okay. So we have seen, right? So if the dependent variable is a t, then this is t prime, right? T prime is some function of t, right? In particular, that function of t, where k and a are constants. That was Newton's law of cooling, right? And that was telling us about the temperature of an object, right, at any time t, okay? Not necessarily a population. Okay, so, but we still have rate of change with respect to time being the intrinsic independent variable, right? The intrinsic, the implicit, the implied independent variable, right? Implicit differentiation. All right, anyway, so here we are, right? We've looked at these kinds of problems. And so let's take another exploration of those guys. Let's just rewrite these, right? Let's rewrite them in this notation. So if we're going to rewrite exponential growth and decay in autonomous notation, autonomous first order ODE notation where x is our dependent variable, then we have x prime is equal to kx. Same equation, right? Okay, same equation. So, so this is exponential growth or decay, right? And then Newton's law of cooling, written in terms of x, would be x prime equals k times, you guys tell me, yep, a minus x, right? X is the dependent variable. Yeah? Okay. So let's explore these a little bit, okay? It's always good to start off with something we have some sense about, okay? So we're gonna revisit these. Now, there's a variety of ways we could revisit these at this stage, right? Both of these are separable differential equations. You could solve them. This one we could solve way back at the very beginning, right? What is the solution of this one? The This was one of our 4 fundamental types of solutions, right? Okay, what would it be? X of t equals c e to the k t, right? Okay, exponential. All right, but that's not our goal. We're going to revisit these through a section 1.2 lens. Slope fields, right? And phase portraits, and what the representative solutions look like, increasing, decreasing, concave up, concave down, equilibrium solutions, right? That's where we're going back to now. And so let's consider exponential growth. Okay, so what's exponential growth? It's the differential equation, the derivative of the dependent variable is equal to some constant times the dependent variable itself. The rate of change is proportional to the function, and the constant k is positive if we're going to have exponential growth, right? Because the solution of this guy, which we just said, right, which we don't care about because that's not what we're doing right now, but if we wanted to write it, would be c e to the k t, right? X is a function of t, okay? We don't care about that though. What do we care about? All right, let's look at the idea of where's our equilibrium solutions? Remember, what's an equilibrium solution? A solution, well, now our dependent variable is x equal to a constant, which makes x prime 0, right? So what are the equilibrium solutions? X equals 0 is an equilibrium solution, right? This guy set equal to 0, x equals 0 is an equilibrium solution, right? X equal to a constant, yes? What about increasing and decreasing? Where are solutions increasing? Well, what do we know about k? K is positive, right? That's what we're looking at exponential growth. And so x prime is positive when x is positive, right? And what about decreasing? X prime is negative when x is negative. Now remember, where is x? What should I label x? Good. Vertical axis, right? This is t. Yeah? So what do I know? I know I have an equilibrium solution. Draw in blue. X equals 0, my equilibrium solution. And then what do I know? Up here, when x is positive, right? Values of x positive, I know my solutions are increasing. And when x is negative, I know my solutions are decreasing. X negative down below the t-axis, right? X is the dependent variable. All right, good. All right, what about concave up? So we want to look at concavity. Concavity, we need the second derivative, right? So we need to take x double prime. K is a constant. So x double prime is k times x prime, right? What are we taking a derivative with respect to? That's the second derivative of x with respect to t, right? We're taking a derivative with respect to t, okay? But what is x prime? X prime is kx, right? When I replace x prime with kx, I get kx. Whoa, let's try that again. I get k times kx. Don't try to skip steps, right? K times kx, which is x prime, which is k squared x, right? What do we know about k squared? Positive, and therefore, where do I have concave up? Concave up, this is positive, so that's going to be positive when x is positive, and concave down when x is negative, right? So I'm increasing and concave up there, and I'm decreasing and concave down there, and so we can draw, this is if we were doing 1.2, right? In 1.2, what are we doing? Well, we're just, we have solutions that do this, right? Okay? But it was kind of a hassle, like looking at these things, but if we actually are careful about it, decreasing concave down, increasing concave up, exponential growth, right? Because we really should, pay attention to the slope slope field to make sure our slopes at each point actually match the slope that it says it would be, right? So that's a lot of stuff in there, right? This is the 1.2 lens, right? That's what we would have done there, versus this is chapter 0, where we just thought about what kinds of functions satisfy this. Now we could solve it with our separable differential equations piece. So again, we see if C is positive, we're up here, and if C is negative, we've got these guys down there. But we don't really care about the solution. We don't need a closed form solution. But this is just a lot of stuff, and so we're actually kind of interested in, well, maybe we could kind of condense this all down into something a little bit simpler to look at, right? And that's our kind of next goal. Maybe I'll do that over here. Okay, can we make this simpler? Okay, let's condense. Condense to something simpler. The beauty, right, what's going to make this simpler? The beauty of an autonomous differential equation, right, is that since the right-hand side doesn't depend on the independent variable, yeah, then the slopes, no matter where, are just going to change with the y, or the x, right, okay? And it'll be the same across the entire set of the independent variable from minus infinity to infinity, right? Because the independent variable doesn't enter the right-hand side of the ODE, so it doesn't change the slope, right? So because of that, we could really just look at like a slice and think about what's happening, okay? So let's think of that problem this way. So now we just have a single, let's just draw a single vertical line, and that's our x-axis really. What do we have, right? X equals 0 is an equilibrium solution. So what is an equilibrium solution? In this context, an equilibrium solution is a solution. Solutions have equations, right? X equals some constant, right? And such that the derivative is 0, right? That's a consequence of this guy being a solution. X equal a constant has the derivative being 0, right? Okay? So that means no change in our solution, right? Now, a critical point, so let's think about this. X prime equals some function of x, right? That's where we are. They're autonomous equations, right? These are examples, but in general, it's the derivative dependent variable, some function of the dependent variable, right? So what is a critical point? A critical point is a point on the vertical axis where f of x is equal to 0. It's a little bit different, right? Okay? Any point on the vertical axis where f of x is 0. Okay? All right, so x equals 0 is an equilibrium solution. It's a critical point. Okay? Now what do we do from here, right? So what do? You find the critical points. Critical points are going to make the derivative 0, right? Okay. And then you examine what happens on either side of the critical point, right? And so the same idea, you can think of a sign chart. I'm gonna write it like this, right? Like a sign chart you would have in calculus. This is a sign chart. This axis is the x-axis, so now I'm writing it horizontal, right? But it's really vertical, yeah? I'm interested in a x prime sign, right? Sign lines of x prime. And 0 is the one place where I know x prime is 0, yeah? And if I'm looking at my x prime over here, we already talked about increasing and decreasing. If x is bigger than 0, then I've got x prime is positive, and if x is smaller than 0, then I've got x prime is negative, right? So what does that mean? X is increasing, and here x is decreasing, right? Okay? So I can put that on here where I'm saying, okay, well, if I'm bigger than 0, if x is bigger than 0, then my solutions are doing what? They're increasing, they're moving away from 0, right? You kind of see that? Right, if x is bigger than 0, what's happening? The solutions, right, are growing, right? They're increasing, they're moving away. And if x is smaller than 0, x is down here, right? Then what's happening? My solutions are decreasing. Yeah? They're moving away from 0, right? Moving away from 0, right? Solutions are decreasing. Okay, and so this little picture tells me the same thing that, well, most of what that picture tells me, okay? A lot of what that picture tells me. So what do we say about this type of critical point? This type of critical point, what happens? If I start exactly at 0 for x, I stay at 0. If I start exactly at 0, right, I stay at 0, no matter what t I'm at. If I start where x is 0, then my solution is only that guy, right? Whether I start here or whether I start here, no matter what t I'm at, right? If I start when the dependent variable is 0, I never change. But what happens if I start just, 10 to the negative 47th away from 0? Well, if I did that, here, if I started here and some tiny little bit away from 0 in x, then what would happen to my solution? It would go away, right? And that's what this is saying. If I start a little bit off of 0 and positive, my solutions are going away. And if I start a little bit off of 0 and negative, then my solutions are going down there. I'm nowhere near 0, right? I don't stay near 0 at all. And that makes this an unstable critical point. Because no matter what it is you're doing, whether you're measuring, you've got units of measurement involved, whatever it is, you're not going to get exact. There's going to be some amount of error involved. And some amount of error causing the solution to be entirely different is bad. That's bad, right? You don't want to have that kind of lack of stable dependence on just being a little bit off with your initial condition. Sometimes that's called continuous dependence on the data. There's a variety of other things associated there too. But we've got, if we're a little bit off, we don't stay here, we go away, right? Does that make sense? All right, and that's bad, right? Because you're never really going to be able to start exactly somewhere. And so it's relatively simple to see right here that as t goes to infinity, where does x go? Well, x of t is going to go to positive infinity if x started out positive, right? If x of 0 was positive, okay, or wherever you want to start, okay? X of 5 is positive. And as t goes to infinity, what's going to happen? X of t is going to go to negative infinity if you start somewhere negative, right? If we want x to go through this point right here, well then what's going to happen? Going off to negative infinity as t. Yeah? Okay? And so the solution becomes unbounded and things blow up and you don't stay near your critical point if you move slightly away from it. That's unstable, that's not good, okay? Okay, so what else can we then say? Let's go look at, let's compare that now with what if we did exponential decay. Let's see if I can avoid doing a whole lot of changes. Let's look at exponential decay. Okay? All right, so what's exponential decay? Well, it's basically k is negative, right? K is going to be negative, yeah? Well, we still have an equilibrium solution of x equals 0, right? Let me just erase the whole thing. And draw another one. What's this axis? Good. Yeah. Okay. So we still have an equilibrium solution of x equals 0. Right? And now what happens, right? Where are solutions increasing? Well, if k is negative, then we need x to be negative for increasing solutions, right? Negative times a negative would be a positive, x prime positive, right? If k is negative, then where would we have decreasing solutions? Where x is positive, yeah? Okay, so what do we know? We've got increasing down here, x negative, and decreasing here, x positive, yeah? Okay, if we go ahead and look at concavity, then we know a little bit more, right, than what we're really looking at over here. So let's go ahead and look at concavity. Same thing, take the second derivative with respect to time. We've got k times x prime, but now, so we've got k times x, right? And now it's k squared. But now, right, this doesn't change at all, right? Because if k is negative, its square is positive, yeah? Okay, and so what we have the exact same thing for concave up and concave down. So we have concave up when x is positive, we're decreasing in concave up, and here we're increasing in concave down. Yeah? Okay? And so let's draw some solutions. Right? This is again 1.2 view, right? Where we're not really doing the slope fields, we're doing more generality with the calculus like we did in the videos there, 1.2. All right, so if I have a function that's decreasing in concave up, right, what does that look like? Decreasing concave up looks like that, yeah? Right? Decreasing concave up. And what does increasing concave down look like? We know solutions can never cross, right? Increasing concave down looks like that, right? So what about this one? Yeah, let's come back over here. What happens now? Well, if we start directly on 0, we stay 0 for all time. Yeah? Okay? 0 is still one of our critical point. But what happens if we start somewhere off of 0 and positive? You know, like here. Oops, that red isn't liking things so much. I'll go with green. What if we start there? Well, then what your solutions, what are they going to look like? That's what's going to happen, right? What happens as time goes on? That solution goes to 0, right? Solutions are decreasing if I'm a little bit above, right? Decreasing if I'm a little bit above, so I'm going down toward. If I'm above, I'm decreasing, yeah? And what happens if I'm below? If I'm below, and I start off, say here, you know, what's going to happen? What's that solution that goes through there? Does this. What happens as time goes on? Whoops, doesn't cross there, right? What happens as time goes on? The solution goes to 0, right? As t goes to infinity, the solution goes to 0. Yeah? Okay? Because what's happening, right? Solutions are increasing below, right? The solutions are increasing below. And so what do we have here? Okay, that's looking a little bit, I'm just going to erase it so you can see it a little bit better now. Here's our critical point. What happens if we're above? Whoops. What happens if we're above? We head toward. What happens if we're below? We head toward, that is called a stable critical point. Let's rewrite this stuff here, okay? What happens as t goes to infinity, x of t goes where? We don't need any of this, right? We don't need to say if x is positive or x is negative. As t goes to infinity, x of t goes to 0, right? All solutions go to 0, yeah? Okay, whereas with exponential growth, we had unbounded growth as t went to infinity. Here, what do we have? We have population goes to 0, right? The population is annihilated, no question about it, right? Okay, now think about how nice that would be for populations of certain viruses. Anyway, so here we go, right? So that's kind of what this is telling you, right? That no matter, as time goes on, you're going to converge on 0. You start off, if you start away from the critical point, you still end up there as time goes on, right? As time gets large. So that's our stable critical point. So this guy is kind of equivalent to that drawing, right? Does that make sense? It's telling you the same information, yeah? Telling you the same information. Not the same, it's telling you some of the same information, okay? But it's simpler to look at. Okay. So I wanted you to make the connection between what we were doing before with phase diagrams, phase planes, based off of the idea of slope fields. Slope fields were 1.2, and then we drew in the representative solutions. Here, the book is also calling these phase portraits or phase diagrams. I'll try to call it a phase diagram because we were calling the representative solutions phase portraits. Okay. So we've talked about exponential growth and decay. Okay. We call that, I think the book calls it stable. It's also called asymptotically stable. Asymptotically stable, right? Why? Because it's stable in a limit as t goes to infinity, right? As t goes to infinity, solutions go to 0. Yeah? Okay? All right. So, population driven to extinction. That would be good for virus populations, right? For virus populations, you gotta be careful what you're modeling, yeah, when you make those claims. Okay, so now what should we do? Let's look at another another example. Okay. Let's look at our Newton's law cooling. Okay, we'll do this one a little bit quicker. We already talked about this guy, right? It's a generalization, really, of this one, right? A generalization, yeah? Okay? You can see how that works. And with Newton's law of cooling, we've already looked at this piece, so I'm just going to kind of talk us through it, and you can kind of walk yourself through drawing or writing out the details of it all. What would be an equilibrium solution? Well, just x equals a, right? X equals a. With this k is a constant, a minus x equals 0. A is a constant, so x equals a is a constant. That makes thus x prime is 0, right? So let's just call this a right here, okay? And so here is an equilibrium solution. X equals a. What does that mean? If at any time t I start on this line, I stay on this line, right? Okay, so let me think about the other idea, our phase diagram. X equals a is also my critical point, right? The point A on the x-axis, yeah? where the equilibrium solution is the horizontal line x equals a, yeah? Okay. So it's not too hard to show that if I'm down here, just to have colors. If you're below A, you're increasing and concave down, and if you're above A, you are decreasing and concave up. Okay? Same way, so what do these guys look like, right? Increasing, same thing, concave down, right? Increasing, concave down, decreasing, concave up. Yeah, you basically just sort of shifted. Yeah, you've shifted up to A. So what has happened in here, right? If we're above A, anywhere above A, solutions are decreasing. X wants to come down. And if we're below A, solutions are increasing. X wants to go up, right? And so tell me here, this little phase diagram gives us a asymptotically stable critical point at x equals A, right? So what is the limit? As t goes to infinity of x of t, we don't need to solve this equation in order to get the explicit x of t. We've already solved it in one of the previous videos. It's Newton's law of cooling, right? So you can go back there and double check. We talked about it then as well. But without even having the explicit function, we can say that the limit as t goes to infinity of this function is A, right? No matter where we start, we're going to end up eventually close to A. Yeah, makes sense? Okay, so that's kind of awesome because you can get information on population dynamics, how things change, without actually solving the equations, okay? Now this is all stuff we've done before, right? Okay, so it's probably pretty good that we also reinforce it. Incidentally, before we jump to the next one, this is called semi-stable. Suppose you have a critical point, and on one side you're going away, but on the other side you're going toward, right? So solutions down here would approach the critical point, and solutions up here would go away from it, right? So it's semi-stable. You're stable if you're below, but you're not stable if you're above, right? And similarly, if it went the other way. In this case, you'd be stable if you were above, but not stable if you were below. Solutions below would go away, solutions above that start above would go toward the critical point as t went on. Right? Make sense? Okay. So that's all possibilities, right? Both to get pointing to the other, pointing away, this, right? Okay. Anyway, here we go. Let's expand now our modeling ability, right? Okay. So with Newton's law of cooling, the coffee cup, you know, the coffee in the cup always approaches room temperature after enough time has passed, right? So here's a new model that we haven't talked about. And this model is used quite a lot. The logistic model, okay, the logistic equation. All right, so what is the logistic equation, right? So I'll write it here kind of like this. I'll write dx dt as given in our book, right? That's what x prime means. Dx dt is kx times m minus x. Okay, so now instead of an exponential growth where the rate of change of a population or thing was just proportional to itself, in Newton's law of cooling, the rate of change with respect to time is proportional to the difference between itself and its environment. Now what do we have? The rate of change is proportional to the product of itself with, well, what is that? The difference between itself and, what is that? Related to this, the environment, well, not so much in these types of population problems. We'll talk about what that ends up being here in just a little bit. We'll take those guys to be positive constants, okay? There are other equivalent renderings of this equation, okay? So let's look at that for a sec. Other equivalent renderings of logistic equations. One is derivative of y with respect to t is y times r minus ay. Okay, so you know that r and a are constants, right? Y is your dependent variable. Another one is also known as the derivative of y with respect to t is r times 1 minus y over k times y, okay? There, r and k are obviously constants. Parameters, right? Parameters. Okay, so let's see. This one is the original, okay? You can go look up quite a bit more on these things. This is from 1838, discovered by Verhulst. Sure, I probably didn't say that correctly. It was a model for fruit flies and flower beetles populations. Model came out 1938. It wasn't until, 1838. It wasn't until the 1930s that there was enough experimental data to validate the utility of the model, right? 100 years later. All right. Anyway, so all of these models are basically the same, these three. They just have a slightly different renderings for different purposes, right? But they all, right, if we compare them to these guys, yeah, these guys, what is the major difference between logistic equations and these guys? What's the major classification difference? I think I heard it. Yeah? Linear, linear, non-linear, right? The logistic model has a y squared, right? Dependent variable squared term in it. It has a linear term on the right side and a non-linear term on the right side. It just depends on where you put the constants and what you call them and what your interpretation is for them. This is actually a capital K here. So, careful. Okay. Anyway, so let's see. Where might this have come from? Before we jump in and dive in and talk about it, let's talk a little bit about where it might have come from. Okay. So if I think about exponential growth, let's write it in this term, right? dy dt is really, if I write it like this, thinking about the original model, ry, okay? And again, you can see some of these details, see a lot more about this in the Boyce and DePrima reference that's also in the book that we talked about at the beginning of class. So dy dt is ry, that's exponential growth, right? R is a constant, yeah? Okay. So what are the units of both sides of this equation? Well, y is whatever you're measuring your population in. Population. T is time. So population per time, right? Numbers per time, right? Okay. And so what are the units of R? What are the units of R? good, well, right, the units of both sides have to match. The units of y are population, right? So units of r are 1 over time. Yeah? Okay. Exponential growth predicts infinite population growth, but we all know that populations don't grow infinitely, that limiting resources end up causing populations to level off, right? Okay? And so, while this is a nice model at the beginning, it's not a good model later. It doesn't do a good job of predicting longer term behavior, right? It might predict what's happening right at the very beginning, but it's not so good, you know, once capacity constraints and more realistic conditions come to play. So what do we do? You know, how did the idea, right, this R, right, so what is R here, right? R is our constant of proportionality, right? It's a growth rate. It's a rate of growth or decline. It makes sense, right, that it has a measure, unit of per time. And so, what is the deal then, right? This constant is sort of nice, right? So the goal with the logistic equation is to come up with the simplest equation that could kind of be like, okay, well, what if we turn this constant into some function, we'll call it h of y times y, right? So that we can take into account that maybe for small values of y, that h of y is kind of like a constant, but then as y gets bigger, right, things change, yeah? And we want to do 3 things. The h of y should be approximately r for y small. We just said that. What else? H of y should decrease as y increases. The bigger the population gets, the less able it is to keep growing. You're going to run out of resources. And then eventually, this guy should be negative for y significantly large, because it's got to drive things down. Things got to die. And the h of y that does these, the simplest h of y that does these guys is that guy right there. R, a constant minus a constant times y. A nice little linear function, but then we're multiplying it times this guy, and that's giving us a non-linear right-hand side, okay? All right, so, you can explore some of that yourself if you like, right? What's h prime of 1? Negative a. So it's a positive constant, right? Okay. All right. So let's see. All of these guys, they all have the form, right? The derivative of y with respect to t is some constant times y plus some other constant times y squared, right? C1y plus C2y squared, right? C1y plus C2y squared. C1y plus C2y squared, right? They all have that same form. It's not convenient to look at it this way. It's much more convenient to look at it in any of these other ways. Okay. So we're going to go back to the logistic equation that's in our book. We're going to look at it in this context. But we could easily well have looked at any of the other views on logistic equation as well. So if you want some more insight into these others, then you can go and take a look at the Boyce and Prima and the references in section 2.5. So if you go to Boyce and Prima, section 2.5, probably in any version of the book, find a cheap one. There are lots and lots of interesting applications of these equations in all kinds of environmental and disease modeling scenarios. Fishing with harvesting, renewable resources, passenger pigeons, human mortality, epidemics, smallpox, you name it. There's versions that these guys will, that these models do a pretty nice job of exploring. We're gonna stop this video now so that I can just come back in a new video and quickly talk about this equation in the context that we just talked about the other two problems. You might want to try for yourself before you watch the next video. See you soon.